You can drive now.
Alrighty, welcome back, everybody. Hope y'all are doing well today. Just wanted to start off talking about the crop project a little bit. I'm just going to continue to ask you all to get on the sign up forum and go ahead and stake your claim on whatever crop you want to look at. I set the due date for November 1st. And I think I've got all the details on there explaining it pretty well. I've got an example of the presentation that I want you to develop. I ask you to write a paper and make a presentation from it. Just for full disclosure, you don't actually have to turn in the paper, so that doesn't have to be, written paragraphs. I would just suggest using it kind of as an outline to make sure that you get the information in your presentation. So we can talk about this more as we get a little bit of extra time, but just go ahead and at least get on there and sign up for the crop project. Look at which areas you need to, I guess, look at. Try to figure out what you need to develop your presentation around, and then we'll discuss it a little bit later at a future date in more detail. But I think everything is pretty well self-explanatory. The second thing I wanted to mention is we do have a lab, another take-home lab, and I'm going to get your lab kits sent off hopefully next week. But this first one doesn't involve doing that. We're going to be working a fair amount doing some lab work with soil stuff. So what I want you all to do is do this first soil lab, just looking at the soil texture, basically. And again, I think it's pretty well self-explanatory, but don't hesitate to contact me if you have any issues with it. Finally, one more reminder, the quiz for climate is due on Sunday night, so just be sure to get that in. And we'll go ahead and get back into the soils presentation here. So we left off talking about, make sure that you guys see that all right?
Yeah. Okay, so.
Okay, good. So talking about soils, we left off talking about soil texture. And so just determining soil texture is actually what that lab is looking at. And we define soil texture as the percentage and ratio of sand, silt, and clay particles. And we can also look a little bit to a lesser extent at things that are larger than sand, like gravel and stones. What's important to look at here is that it's defined by the size. So we're looking at not necessarily it's a different particle. I mean, it is, but it's the size that they class it as. So we look at gravels and stones as anything that's greater than 2 millimeters in size. Sand being between 2 millimeters and 5/100ths. Silt between 5/100ths of a millimeter and 2,000ths of a centimeter, and clay anything less than that. So sand, silt, and clay, very important for determining soil texture, which actually determines a whole lot of different properties of your soil. So our lab is basically determining your soil texture by doing a jar test. And it's a very simple, easy test to do, but I think it's invaluable. You actually use this soil texture triangle that the USDA publishes to determine what it is exactly. So we've had mixes all over the board, really. We've had a lot that are kind of in this middle area, the loam soil, which is kind of not necessarily an even mix of all three, but what we consider a good balance of all three, a balance of the properties, I should say. So, and that's what we really want in terms of an agricultural soil, is a good loam. But this is something that you can't change, and that's why we really need to look at it. You cannot change your textural components in a field setting. In a controlled environment agriculture, you can manipulate that, but in the field setting, you can't really change this. You can make soil amendments that will help to change some of the soil properties, but you won't actually be able to change the texture. So very important to look at. Here, those soil properties are influenced by the texture. So this table is just looking at these different particles and how they kind of impart different properties. So sand, we think of mostly for drainage. It's excellent for drainage, excellent for providing air pockets, but it's low in this cation exchange, which we'll talk about here in a minute. For now, just think of cation exchange kind of sort of like fertility. Sand is easily erodible. It's very permeable, so it has low water holding capacity. The silt loam, as you can see here, it's a good balance of everything, basically. So on the opposite extreme, clay is very poor for aeration, but it's high for cation exchange. It's high for water holding capacity. It's difficult to till, though. So as you can see, silt, of course, is kind of the in-between textural class, and a silt loam has some sand, some silt, and some clay. We really need all three, and I feel like clay gets vilified often for, well, especially in our areas, in our physiographic provinces, we tend to have a fair amount of clay soil, and because of that, poor drainage kills a lot of plants. It's limiting for our ability to conduct agriculture. So we think of clay as being the bad guy. On the coastal plain, though, which is one of the most important agricultural areas for Virginia, they have more sandy soil. So in some cases there, sand might be the villain. Nonetheless, none of them are better or worse. We really need all of them. We need a little bit of both sides, and ideally need to be kind of moderate and in the middle. All right, so looking at texture affecting the soil aeration, plants do need oxygen in the root zone, and that's for respiration, so that those roots can breathe and actually be able to take in water and nutrients. So if we don't have good respiration due to, say, lots of clay in the soil and too much water, then we get root rot. It's also important to note, though, that of course different plants are adapted to different soil types. So it's not everything, it's just to look at the different soil textures that you have, and which you are going to have different soil texture probably on a large scale. Say if we're looking at acreage, you usually have more than one soil type on a farm. So different pockets of different places might be better suited for different plants. And also the ease of the tillage. So actually preparing the soil, which we'll talk about in more detail later on. But in terms of preparing it, it is also going to be influenced by the soil texture. The sandy and loamy soils are going to be easier than clay soils to till. So generally, we think of the loam soils as being the ideal agricultural soil. So we think of soil texture as the kind of individual particles and the arrangement of those particles, but we stack those particles together. So we look at these individual particles as the texture, but then as those particles kind of aggregate and clump together into these secondary units, we call that a PED, and that's important for soil science to study the PED. As you stack these different PEDs together, then they aggregate and make kind of the soil profile. They make the aggregates, which are the secondary unit of soil structure. And that also is going to give it specific characteristics. So we have just the texture, and then the texture working together to create the structure. And we're going to look at that in terms of the size and the form of the aggregation to get the structure of soil. And we're going to get these also as varying in size and shape. So here's just a look at kind of the most, I guess, common structural forms. And there are some intermediate types of soil structure as well. But we look at these as kind of being the definitive types. Platy here, prismatic, columnar, angular, block, subangular, blocky, and then finally granular. So these are the different aggregate soil structures that we have, and really what we see, this is all pretty much your kind of what you would have in a natural, unaltered soil. That's what it's like before activity. And then you get more of this subangular blocky with activity, but maybe not the best type of activity. What we really want, though, the ideal structure for agriculture is this granular soil. That's what we are looking for, and that's kind of what we create when we till. When we prepare the soil, we're getting this more granular. If we didn't do it very well, then we get this subangular blocky. Granular we're going for because it gives good soil to seed contact, makes a good seed bed so that plants can germinate, seeds can germinate, and plants can grow. Good, conducive to root growth. Good pockets of air as well. And you can kind of see in these other soil structures, you probably don't have good air pockets in them. So again, these are more natural. These are kind of more, we can have these in natural settings, but what we're kind of going for is this granular type of soil structure. So of course, soils form over time and through weathering, basically. So as soils weather, they break down from the parent material, from that rock into soil. And that's affected by climate, by the temperature, and weather is going to affect how these different soils form. And we're not really going to get into this in this class, but what they have here, oxysols and spodosols, those are totally different types of soil, and they just use these as examples of different orders of soil being formed under different climates. But it's really not just the climate, it's everything else as well. What was the parent material? What is the vegetation that was growing there, which is kind of a give and take too. So here's just an example of that. You would see, in this case, we have a spodosol. And what we get here is that we have these organic compounds that are produced, the decaying conifer needles that affect chemistry of the soil. And in this case, we get this E horizon. So we talked about the A, B, and C. There's also an O, which is organic matter. That's usually closer to the top. And then this E horizon, which is usually below the topsoil but before the subsoil, as you can see in this image. And this E is the eluviated horizon. And basically what we're looking at for eluviation is just this movement of chemicals, in this case, but also organic matter being deposited into a different zone. And that will move down into the B horizon as well. But usually we get this white zone that is basically just this carbonate, these aluminum compounds that we have moving into a zone below it. So it looks white when we see it. And that's characteristic of that one type of soil order, but we do see it in many other soil types. Speaking of chemistry for soil, we do need to take a look at the pH. So pH we look at as either how acidic or alkaline a soil, or really anything else is. We use pH to look at water as well. And pH I think of literally as the power of hydrogen. It's a negative logarithm of the activity of hydrogen ions in whatever solution it is, soil, water, air. So we have this pH scale, and these values of pH are going to vary from soils, from place, from climate, from plant type. But nonetheless, it's going to range really in the soils world, probably kind of more here in this area. And ideally what we really want is right around neutral for the greatest variety of crops. Lower on the pH scale is more acidic, higher on the pH scale is more alkaline. And we could have as low as a 4 and up to a 10, but usually the range is more narrow than that. Because we have rainwater is actually naturally acidic. If you think about it, H2O, it's got that 2 molecules of, or 2 atoms of hydrogen in there. So it's able to impart more hydrogen, which makes it more acidic. Think of, again, that power of hydrogen. And it's really this balance between hydrogen and hydroxide, which hydroxide, the chemical is OH, and it's a negatively charged ion. So really we're looking at this as a ratio of hydrogen ions to hydroxide ions in whatever medium we're looking at. But nonetheless, it's important to look at this pH for what kind of plants we can grow best, and also how well plants will grow. So most plants do not grow well if it's highly acidic or highly alkaline. Plants, the widest variety plants will grow from 5 to 7, but most plants actually have a slightly more narrow optimum pH. So optimum being, of course, the best. That's what they really want. So there are some examples, of course, of things that like it low, like blueberries or cranberries prefer a lower pH. Some things we can actually grow better at a lower pH, even though they can stand a higher pH, like potatoes. And I say that because one of the common issues with potatoes in our region is scab, and it's a disease of potatoes. But if you have it acidic enough, you don't get scab. So the potato doesn't necessarily have to have that low pH to grow, but to get the optimal crop, it's better to grow it at that low pH. Notice that we go a little bit more on the acidic side. We don't really go much on the alkaline side. There are, of course, some crops that do prefer slightly alkaline or more. Things like beets, your brassicas like broccoli, cabbage, cauliflower, etc. Those like it a little bit more basic, a little more alkaline. But again, they don't have to have it that way. So we have kind of more narrow ranges that the plants prefer, and get them to optimally grow. We try to get that pH range. Generally in our region, in the mid-Atlantic, we have higher amounts of moisture. It's fairly humid. So our soils are naturally a little bit more on the acidic side, probably kind of more on this 5.5 range. So if you think of, say, growing a pasture grass, like let's say Timothy or alfalfa. If we go down here, Timothy still likes it slightly acidic, probably prefers a little bit more basic though. Alfalfa, a little bit higher on that pH scale. So to get those to grow, we need to add lime in order to increase the pH. So soil texture isn't something we can change. Soil pH is something that we can change. It's not super easy to change it on a large scale, but it can be done. So why do most plants prefer around neutral? Because most nutrients are available around neutral. So if you look at this, this table is looking at that, pH scale and which nutrients are more or less available when it is more acidic or more basic. And so I think that explains a lot when we look at those plants, because sure, there are some of these nutrients like iron, manganese, boron, copper that are more available if it's acidic. And then there are some of these like boron actually has kind of this, it's kind of broken into two. It's not as available right at neutral, more available strongly alkaline. Some things like molybdenum maybe more available, more alkaline, but for the greatest range of nutrients, it's right around neutral. So that's what we're going to go for crop production in general. That's a good starting place. I would always say too that it's a little bit easier to raise the pH than it is to lower it, because lime is usually fairly plentiful around the country, especially in the eastern U.S. Because we got limestone, but we don't have as many options for lowering the pH. You could add like peat, or you could add sulfur compounds to it. They're not quite as available and easy to lower that pH. So if you start lower and try to raise the pH, it can be easier for crop production. So I kind of already mentioned here that the soils in different climates kind of develop into different pHs. So if we have high rainfall, high humidity, we've got lots of hydrogen, we tend to get a little bit more acidic. And in arid climates, they tend to be a little bit more alkaline. What we need to look at in terms of trying to change the pH is this term here, buffering. So buffering is just the ability for a soil to resist changes in pH. So the fine textured soils are more resistant to buffering than the more coarse soils. So usually we think of fine textured soils as being heavier clay soils. So it's harder to change the pH of a clay soil, harder to buffer it. Looking at the cation exchange capacity, CEC is another important property. And it's important because really it is the ability to attract and hold cations. And cations are just positively charged ions, which if we look here in the image, we got NH4, calcium here. Notice these are positively charged. Ammonia and calcium are both positively charged in their kind of natural form. So cation exchange capacity means that they can hold on to these cations. We also look at anion exchange capacity, which anions are negatively charged. So we kind of need both of them, because there are some nutrients that are anions and some that exist as cations. An important property here, though, is that clay and humus. So clay and organic matter are those that are most responsible for holding on to cations. And actually, clay and humus together. So clay and organic matter together make a good form of actually holding on to both water and cations in a soil. We look at cations being exchanged as basically the soil solution. Water moving through the soil, it is going to pick up and move these cations. And that's how plants get their nutrients, is through water. So they're going to suck those nutrients out of the soil solution as it's moving through there. So it's important that soils be able to hold on to those cations, but also be able to exchange them and move them into water. So there are a few that we look at as anions, so it's important, especially with nitrate. And if you're using nitrate-based fertilizers, then you want a good anion exchange capacity. So cation exchange capacity is going to be greater under alkaline generally than acidic conditions. That's just a general thing. It's not always the rule. Important to look at though. So pH also affects cation exchange capacity. Saline soils, those that are kind of salty, they have large quantities of soluble salts, and generally when we apply fertilizers, depending on what the fertilizer is, of course, manure is not, natural forms of the fertilizers are not, but any synthetic fertilizer, we're actually adding soluble salts, and this can be good, can be bad, so don't overdo it. Everything in moderation, especially when it comes to agriculture. So when we're talking about the soluble salts, some soils are just naturally saline and or sodic. The difference there between sodic soils and saline soils is just there's a different percentage of cation exchange sites and what actually occupies those. So in sodic soils, we have those as being occupied by sodium ions. As saline, it could be any other salt. So generally, we don't want high amounts of soluble salts in our soils. We want to leach these off and allow them to drain, even though some of these are good, especially when we look at like calcium, magnesium. These are very important micronutrients for the growth of plants. All right, so the chemistry of soil also has a lot to do with the soil organisms. And if we look under a microscope at soil, then we will see that we have all different levels. There's really a whole food web going on in the soil. We have beneficial animals, things like earthworms, for instance. Burrowing animals can be good. They can also be bad. And moles and voles, of course, larger organisms living in the soil. But of course, we can get down to that microscopic level. We have all kinds of different bacteria, fungi, really a little bit of everything. All forms of life are represented in the soil. And I think I mentioned it on Monday, but they say that 1 teaspoon of good soil with lots of organic matter in it can have over 1 billion microorganisms. So it's good to have a lot of them, because then we'll probably have a better balance of the good guys and the bad guys. So the kind and the amount of those organisms present is going to depend on, of course, the climate, what plants are there, the pH of the soil, the fertility level, the temperature, the moisture. The biggest thing, though, that determines soil microorganisms is the OM, the organic matter. So like I said on Monday, one of the best things you can do to make a better soil is add organic matter, whether that's in the form of manure or a cover crop or compost. Even just mulching can add organic matter to the soil, but organic matter is food for the microorganisms, and especially for the good guys. So it's important to add that to soil. So let's take a look at some specific soil organisms. We already talked about rhizobium when we were talking about ecology. It's a nitrogen fixing bacteria. So it's taking it out of the air, and it is actually fixing that nitrogen in these little nodules that you see on the roots of leguminous plants. There's some other plants other than legumes that have that as well, but think of like alfalfa, soybeans, clover. Those are all legumes, and they put that nitrogen, take it out of the air and put it into the soil. So that's a very important process that microorganisms do. Tiny little unicellular organism does a lot for the plants that we grow. It means you have to apply a lot less fertilizer. We also have sulfur oxidation, nitrification as processes carried by soil bacteria. These are essential to the plants that we grow. They're not all good guys, though. We have things like nematodes that can, and their nematodes are not just bad. There are some good and some bad nematodes, but we tend to think of nematodes as bad because a lot of them feed on roots. There are actually some nematodes that feed on other nematodes too. And think of nematodes kind of like a microscopic worm. It's like a little worm floating around in there. It is actually an animal. We have phylloxera, which is kind of like an aphid. It feeds on grape roots. So what they've done to figure that out in vineyards is use phylloxera resistant rootstocks, and they actually graft their wine or table grape producing varieties onto these rootstocks to try to prevent phylloxera. We also have all kinds of different pathogen based soil borne bacteria and fungi, diseases. So in that case, we do the same thing. A lot of times we will plant resistant rootstocks or resistant varieties to try to prevent that. And that's something that is in tomato production. I think someone did sign up for tomatoes to look at for their crop project. Something to look at there is how a lot of growers are now grafting like the heirloom varieties onto these like hybrid resistant rootstocks. So I mentioned organic matter is very important for many things. I mean, one, for the biology, but it also is very important for the chemical, for the cation exchange capacity. And I think when you combine it with clay, so a colloid of organic matter, humus, with clay is one of the best in terms of having cations and actually being able to exchange them. But it also improves the drainage of clay soil, so it also affects the physical properties. And it is the food and energy for the soil organisms. And what we look at for organic made of carbon, hydrogen, oxygen. That's why we call it organic, because it's made of these three atoms, these three elements that really are basically the elements of life, C, H, and O. More on that later. So organic matter is always in flux in the soil because it's being eaten, broken down by the organisms in the soil. And also that carbon, hydrogen, and oxygen is being taken up by the plants. So the speed of that organic matter decomposition, which when it's fully decomposed, it is humus. And that doesn't change as much. But it's the organic matter that's in flux being turned into humus that is very changing. So that's going to vary according to its chemical composition. So for some things that have simple carbohydrates, it's very quick. For other forms of organic matter that might be higher in fats or lignins, it can be slow. So here I'm thinking kind of more of the herbaceous plants for the simple carbohydrates, more green matter, more of the brown dry stuff for the fats and lignins, woody plants material. So again, after we have that complete decomposition, we get humus, and that becomes an amorphous colloidal substance it is resistant to further decomposition. It can still be utilized by plants though. So it does improve soil structure, increases water holding and cation exchange capacities. It's kind of interesting because while it does increase water holding capacity, it can also improve drainage. So it just kind of depends on what you want, and it does both really. When we look at soil in terms of the chemistry and the elements in the soil, we look at a close relationship between carbon and nitrogen. And this also affects the decomposition of matter in the soil. So we look at that as the C to N ratio. And generally in the soil, it is fairly constant around the world, but we see variations in it correlating with the climate, with temperature and rainfall, having a bit of a lower C to N ratio in arid and warmer regions than that in humid and cooler regions, because it's not going to be able to decompose quite as much. And we can kind of see that in this graph here, and how it changes also seasonally too. So as the temperature increases throughout the season, we're going to have more activity in the soil of organisms. Even though soil temperature at a certain depth is stable, we look at that as being in our region, 6 to 8 feet deep. Above that, the soil temperature is fluctuating. So once the temperature warms up, we get more activity in the soil, and we get that carbon and nitrogen in flux. So we have nitrogen is very important because it is the primary macronutrient, the one nutrient that plants need most. N, P, and K. We look at phosphorus and potassium is very important as well, but nitrogen is important because it's actually in chlorophyll molecules. And it can be tied up by organisms causing decomposition depending on what the carbon to nitrogen ratio is. If it's really high in carbon, then it's going to tie up that nitrogen, which means that it might not be available at a certain time, but it will again be released once those organisms do die off. They basically eat it, immobilize it, and then when they die, it releases that nitrogen. So we add organic matter as a way to kind of also sort of save that nitrogen. Nitrogen is also the most mobile of our nutrients, so it quickly moves through the soil. So soil properties, some soil properties anyway, do change fairly constantly, but we can maintain soil properties by the way that we manage soil. So naturally, upland soils are going to experience natural erosion just by climate and weather, but we minimize that by vegetative cover. One of the best things we can do to keep soil in place is keep plants on it, keep it covered. When that cover, whether it's a crop, a cover crop, mulch even is also cover. If it's removed by fire or flood, then that soil surface then becomes exposed directly to the erosive forces of wind and rain and water runoff. So accelerated erosion can remove soil faster than new soil can form, which is going to reduce the depth of a productive topsoil. We're losing topsoil through the effects of erosion. The subsoil layers, the B horizon, is not as prone to this as the A horizon. And again, we do have some root growth into the B horizon, but generally we think of it as undesirable for crop production. So we want to keep topsoil in place, and we need to do that primarily by keeping cover on the soil to prevent erosion, especially if we're growing crops in any kind of area that has a fair amount of topography. If you got slope to it, soil is more prone to move just because there's more gravitational forces there. So stop soil erosion, plant cover crops, or mulch your soil. And that brings us to the end of this presentation, this section of soil. We'll actually come back and talk a little bit more about soil and how we manage it a little later on. And we'll have kind of our lab component. We'll be looking at soil for a little while through our labs. So we have a couple of different labs associated with soil. Some of these that you can do from home, just from the computer. Some of these which you'll actually have to get out and do some digging in the soil. And also some that will require that lab kit that I should be sending out to you guys next week. All right, so anybody have any questions, comments, or concerns? Soil makes the world go round. It's, I think, along with water, one of our most important natural resources, and that's why the Soil Conservation Service was born in the early 1900s, kind of as a response to the Dust Bowl, where we were having major erosion issues in the Midwest. The Soil Conservation Service became the NRCS, the Natural Resource Conservation Service. I think that was in the 60s that it kind of switched over. And NRCS today is a very important organization for you guys because they have a lot of resources for us. They are kind of the definitive resource in terms of looking at soil and learning how to manage it better. But there's also a lot of good opportunities that the NRCS will actually reward farmers for taking care of those natural resources. And some programs, there's an EQIP program, which is a cost share program where they will actually pay up to 80% for fencing and cover crops, making a paddock system for your livestock. They'll plant trees for windbreaks, fruit trees just for wildlife and to help stop erosion. They'll also do some water systems, help you with that. And you can build a hoop house too for next to nothing through that program. So if y'all have land or are interested in it, holler at your local NRCS agent and get on the list for the EQIP program. It's pretty much free money, so take advantage of it. All right, I guess I'll let you all go. Don't forget the quiz. Don't forget the crop sign up. Otherwise, have a great rest of your week. We'll see you next week.
Bye.